What would happen if Earth were no longer protected by Jupiter? For more than 4.5 billion years of the solar system's existence, Jupiter, a planet with 318 times the mass of Earth, has quietly served as a colossal gravitational shield. Without it, the orbital structure of the solar system would be less stable, bringing a greater risk of collisions among the planets. And if Jupiter were to vanish, studies suggest the frequency of impacts on Earth could rise significantly. Would life have survived until today, or would Earth's history have been rewritten by catastrophic collisions? A clear demonstration came in July 1994, when comet Shoemaker, Levy 9, was torn apart and crashed into Jupiter, releasing energy equivalent to millions of nuclear bombs. It was no longer a single celestial body, but shattered into more than 20 major fragments, stretched across space like a colossal chain, like a doomed train racing toward an ending already written. Then, from July 16 to the 22nd of July 1994, each fragment began striking Jupiter at speeds of roughly 60 kilometers per second. It was not one explosion, but a relentless sequence of impacts lasting for days. Every collision released energy equal to around 6 million megatons of TNT, hundreds of thousands of times more powerful than the Hiroshima atomic bomb. When the largest piece, known as Fragment G, slammed into the planet, it created an enormous fireball rising thousands of kilometers high, piercing through Jupiter's dense cloud layers and leaving behind a dark scar larger than Earth itself. Those black marks did not disappear quickly. They remained for weeks, even months, drifting across the violently swirling face of the giant planet, like the lingering traces of a battle we had only just managed to witness. It was the first time in history that humanity directly observed a planet in our solar system absorb a chain of impacts on such a scale. But what makes this event truly haunting was not Jupiter. It was a simple question. What if Jupiter had not been the target? If even one of those fragments had struck Earth, the consequences would have gone far beyond a single explosion. Shockwaves would have raced across the planet within minutes. The heat would have been enough to ignite forests on a global scale. Dust and gases thrown into the atmosphere would have blocked sunlight, triggering an impact winter lasting for years, a scenario that unfolded 66 million years ago when the dinosaurs vanished. But Shoemaker-Levy 9 was not a lone object. It was a chain impact event. This collision revealed a cold truth. Dangerous celestial bodies like these are not rare. They exist, moving through the darkness, and sometimes all it takes is a small shift in orbit to turn them into a global catastrophe. And somewhere within the solar system, Jupiter stood there, not as a conscious hero, but as a colossal gravitational force, silently absorbing threats that might otherwise have come our way. But if that gravity did not exist, if this invisible shield were removed, would Earth still have been so fortunate? At first, you would notice nothing changing. The planets would still circle the Sun, and Earth would continue along its familiar orbit, but deeper out, in the region between Mars and where Jupiter once existed, the asteroid belt would begin to awaken. It is currently controlled by gravitational resonances with Jupiter, especially in areas known as the Kirkwood gaps, where asteroid orbits have been cleared out by the repeated effects of gravity. These regions act like invisible fences, keeping most objects from drifting into the inner solar system. But when Jupiter disappears, those fences disappear with it. Simulations show that within only a few million years, an extremely short span on the cosmic timescale, the orbits of millions of asteroids would begin to turn chaotic. With no stabilizing force, they would be disturbed by small gravitational interactions, gradually accumulating over time. Then, some of them would begin to be thrown into paths that cross Earth's orbit. According to orbital dynamics studies, the frequency of hazardous objects entering the inner system could rise by 2 to 10 times, depending on the model and the starting assumptions. That means events like Chicxulub, which occurred 66 million years ago, may no longer be rare, but become a repeating part of planetary history. Farther out, at the edge of the solar system, the Oort cloud and the Kuiper belt hold billions of comets. In the current system, Jupiter serves as a control gate, either bending their trajectories, ejecting them from the solar system, or holding them in place. When that gate vanishes, nothing remains to stop them. Jupiter is not merely a planet. It is a colossal gravitational resource, containing roughly 70% of the total mass of all the planets in the solar system combined. Its presence creates a stable structure, a system that filters and guides dangerous objects from the outer regions onward. Without it, the solar system would no longer be a balanced system, but a chaotic dynamical environment where orbits are constantly broken apart and rebuilt. Jupiter does not save Earth in a direct sense. It creates the conditions that make major catastrophes rare. But how can one planet control the paths of billions of objects across distances of hundreds of millions of kilometers for billions of years? Jupiter's immense mass bends space itself, creating effects such as slingshot and capture. And those very mechanisms have shaped the fate of the entire solar system. When you look at Jupiter, you are not simply looking at a planet. You are looking at a colossal gravitational field, a structure large enough to bend the paths of everything that passes near it. With a mass equal to more than 318 Earths, Jupiter is not only the largest planet, it contains nearly 70% of the total mass of all the planets in the solar system combined. In physics, mass is the ability to curve space-time, a core concept from Albert Einstein's general theory of relativity. When an object has enough mass, it does not merely pull other objects toward itself, it changes the very shape of the space around it. When Juno entered orbit around Jupiter in 2016, what it discovered completely changed the way we understand this planet. Before Juno, many models assumed Jupiter had a clear, solid core, a dense mass of material at the center, surrounded by layers of gas. But Juno's gravity data revealed a very different picture. Jupiter may not have a solid core in the traditional sense. But Juno's gravity data revealed a very different picture. Jupiter may not have a solid core in the traditional sense. Instead, it appears to have what scientists call a fuzzy core, where heavy material is not concentrated into a separate central mass, but gradually mixed into the outer layers. This means Jupiter is a continuous system where matter slowly transitions from gas into denser forms as you move deeper inward. Juno also found that the cloud bands we see at the surface, those orange, white, and brown flowing stripes, are not merely surface features. They extend downward roughly 2,000 to 3,000 kilometers beneath the visible clouds. This suggests Jupiter's wind systems are not a thin shell like those on Earth, but immense flows reaching deep into the planet itself. These winds reach speeds of 100 to 150 meters per second, and remarkably, they remain stable over long periods of time. Unlike Earth, where most energy comes from the Sun, Jupiter radiates more energy than it receives. The planet's slow contraction under its own gravity, a process known as Kelvin-Helmholtz contraction, continuously releases energy, feeding enormous internal convection currents. And those deep motions create something even more important, a stable and long-lasting gravitational field. But perhaps Juno's most astonishing discovery lies in Jupiter's magnetic field. Jupiter's magnetic field is not only powerful, but highly asymmetric. This is a sign that deep inside Jupiter exists an extreme dynamical system where matter, energy, and forces interact continuously, creating a structure stable enough to maintain gravitational influence across the scale of the entire solar system. But if the outside is only swirling clouds, then what is truly waiting deep within, and what would happen to any object, an asteroid, or even a probe, if it fell into this planet? At the outer edge of the solar system, where sunlight has grown faint, two enormous reservoirs of ancient material exist: the Kuiper Belt and the Oort cloud. All it takes is a small disturbance, from the gravity of a passing star or a distant celestial interaction, and some of those objects begin a long journey inward, racing toward the sun. And along that journey, they must pass Jupiter. At an average distance of about 5.2 AU from the Sun, Jupiter sits in a strategic position between the source regions of hazardous objects and Earth's orbital zone. When a long-period comet from the Oort cloud enters the inner solar system, it often travels at tremendous speeds, reaching 50 to 70 kilometers per second as it approaches the planetary region. Once it enters Jupiter's vast gravitational sphere of influence, the object usually falls into one of three main scenarios. The first scenario, it is pulled in and collides directly. These objects simply disappear, absorbed by Jupiter's atmosphere, which stretches thousands of kilometers deep. The second scenario, temporary capture. The object is drawn into a new orbit around Jupiter, becoming a short-period comet or even a temporary moon. The third scenario, its path is bent and deflected. This is when Jupiter functions like a navigation machine. According to orbital dynamics studies from NASA, a significant percentage of long-period comets are removed from the inner solar system this way before they ever become a real threat. This is not a rare event, but a process that has continued for billions of years. Jupiter operates like an incoming filtration system. Every object entering the solar system must pass through its zone of influence. There, many dangerous trajectories are altered, eliminated, or destroyed before they can move close to Earth's orbital region. This greatly reduces the number of objects capable of colliding with our planet. Not every object is stopped. Some still slip through, and those are the ones that created the rare impact events in Earth's history. However, without this filter, that number could rise many times over, enough to prevent complex life from ever having a stable chance to emerge. And then, an image begins to take shape. But if Jupiter can influence objects from such great distances, then how large is its true zone of control? An invisible boundary, yet once you cross it, your orbit no longer fully belongs to you. That boundary is the Hill sphere, the region of space where Jupiter's gravity dominates over the Sun for nearby objects. It is not a physical surface, but a gravitational territory, where anything that enters is drawn under the direct influence of this planet. Its Hill sphere has a radius of about 50 million kilometers, a distance greater than nearly 1/3 of the space between Earth and the Sun. If you placed Jupiter at the center, its zone of influence would cover an enormous region, far larger than that of any other planet in the solar system. What makes the Hill sphere important is not only its size, but what happens inside it. Imagine a comet or asteroid entering the solar system from a great distance. While it remains outside Jupiter's Hill sphere, its path is governed mainly by the Sun. Then Jupiter's gravity begins to dominate locally, and from that moment, the object's orbit is no longer stable. It may be pulled off course, slowed down, or accelerated depending on its angle of approach. Some objects begin circling Jupiter, becoming temporary moons. Others are drawn deeper inward, unable to escape. And some have their paths bent enough that they never again head toward Earth. The crucial point is this: the process happens very early. Earth's Hill sphere is only about 1.5 million kilometers, more than 30 times smaller than Jupiter's. That means Earth's ability to control the surrounding space is extremely limited. By the time a dangerous object comes near Earth, it is often already too late to redirect it in any significant way. We do not have a large enough buffer zone for early intervention. Jupiter does. It possesses a planetary scale control region. Scientists have found that many of the objects most strongly affected are those entering the outer edge of the Hill sphere. This is where orbital changes occur subtly, yet decisively. A small initial deviation can lead to a completely different outcome after millions of kilometers of travel. A slight shift can mean the difference between passing safely by Earth and striking it directly, and that is the key point. Jupiter's Hill sphere is not merely a zone of influence. It is an early defensive layer, where dangerous trajectories are detected and altered from far away. requiring only gravity that is stable, continuous, and strong enough. How can a gas giant with no clearly defined solid surface maintain such a stable and powerful gravitational field for billions of years? It may be far more terrifying than imagined, because Jupiter is a gas giant, yet the word gas can be misleading. The deeper you go, the environment does not become lighter or thinner. Instead, it becomes so extreme that the familiar rules of matter begin to change. An asteroid entering this world no longer falls the way it would through Earth's atmosphere. It begins to experience crushing friction, compression, and rapid heating, as if being burned from every direction at once. Deeper down, at depths of several thousand kilometers, pressure rises to hundreds of thousands of times Earth's atmospheric pressure. There, hydrogen, the element that makes up most of Jupiter, no longer exists as an ordinary gas. It transforms into liquid hydrogen. If an asteroid were somehow still intact by that point, it would be crushed, torn apart, and absorbed into the surrounding environment. Go deeper still, tens of thousands of kilometers beneath the cloud tops, and the pressure climbs to millions of times that of Earth. What would happen if the space around Jupiter were governed not only by gravity, but also by an invisible shield powerful enough to swallow the solar wind itself? Imagine drifting through space, millions of kilometers from Jupiter. There is nothing visible to the naked eye, but if you could feel magnetic fields, you would realize you were entering an entirely different region of space, a colossal bubble surrounding the planet known as the magnetosphere. Jupiter's magnetosphere is unlike that of any other planet. It is about 20,000 times stronger than Earth's magnetic field. And if it could be seen from Earth with the naked eye, it would appear many times wider than the moon in the night sky. On the side facing away from the sun, this magnetosphere stretches into a tail hundreds of millions of kilometers long, extending beyond the orbit of Saturn. The source of this power lies deep inside Jupiter, in the electrically conducting layer of metallic hydrogen we explored earlier. As the planet spins at extraordinary speed, completing one rotation in only about 9 hours and 55 minutes, this moving conductive material continuously generates a gigantic electrical engine known as a planetary dynamo. The result is a magnetic field that is not only powerful, but intensely dynamic. Charged particles are then trapped within this field, moving along magnetic lines and accumulating into enormous radiation belts, similar to Earth's Van Allen belts, but vastly stronger. This is why the Juno spacecraft had to be built with special radiation shielding, and even then could operate only for limited periods while flying close to the planet. But the more important effect is indirect. Jupiter's magnetic field does not directly block asteroids like a physical shield. It does not deflect the paths of giant rocks, but it shapes the space environment through which those objects travel. Within the magnetosphere's zone of influence, charged particles, plasma, and even cosmic dust are guided in complex ways. This creates a dynamic environment where energy is redistributed, where electromagnetic interactions can alter the state of matter before it moves deeper into the solar system. In other words, Jupiter does not govern only through gravity, but through an invisible field of energy. And there is another remarkable detail. This magnetosphere is tightly linked to Jupiter's moons, especially Io, one of the most volcanically active worlds in the solar system. Io ejects tons of material every second, forming a plasma stream that feeds the magnetosphere, making it even stronger and more complex. This is no longer a single planet. This is a vast electromagnetic system where the planet, its moons, and the surrounding space interact continuously. And when you step back and see the larger picture, a question begins to emerge. If Jupiter can shape space in this way, if it can trap, accelerate, and distribute energy across hundreds of millions of kilometers, are all of those effects always beneficial to Earth? Or in some cases, could these same mechanisms accidentally create danger? Because at this scale, nothing is absolute, and that is where the story begins to change, when the Guardian can sometimes become a source of chaos. We have seen how Jupiter captures, bends, and absorbs dangerous objects, but another mechanism, more subtle and more silent, is constantly unfolding in the darkness of the solar system: gravitational resonance. Imagine an asteroid orbiting the Sun within the belt between Mars and Jupiter. Its orbit appears stable, but only to a point. Each time it completes a revolution, Jupiter's gravity, though far away, still gives a gentle tug on its path. This is orbital resonance. The effect is like pushing a swing in perfect rhythm. At first, the motion is small. But over time, the amplitude grows until stability is lost. Within the asteroid belt, such regions are known as the Kirkwood gaps, zones where almost no objects remain in long-term stable orbits. Because anything that enters these resonances has its orbit gradually excited and pulled away from its original position. According to orbital dynamics, studies from NASA and the Jet Propulsion Laboratory, a significant portion of near-Earth objects, or NEOs, originated in the asteroid belt and were driven into Earth, crossing orbits through resonance mechanisms with Jupiter. This leads to a difficult truth. Jupiter does not only filter threats from the outside. Sometimes, it also creates threats from within. A system large enough to control billions of celestial bodies cannot operate in only one direction. Modern models show Jupiter's role is dual. In many cases, it reduces the number of long-period comets from the Oort cloud entering the inner solar system, a clearly beneficial effect. But for asteroids in the main belt, it can increase the probability that some objects are diverted into threatening paths. Despite those dangerous pushes, most studies still indicate that Jupiter's presence lowers the frequency of catastrophic impacts on Earth, compared with a scenario in which it did not exist. And when you look deeper, without those oscillations, those pushes, those redistributions of orbit, would the solar system ever have reached the stable state we see today? This is no longer the story of a planet that protects. It is the story of a complex dynamical system, where life may survive only when chaos is controlled, but never fully removed. The existence of life on Earth is not purely a coincidence of biology, but the result of a harsh mechanical order within the solar system. though Jupiter is not an absolute shield, because that same gravity can sometimes push an object into a dangerous orbit. Statistically, it has reduced the frequency of catastrophic impacts to a level low enough for life to form and evolve. When we look at Jupiter, we do not simply see a magnificent planet, but a silent guardian shield, proof that for a blue world like Earth to exist, the universe required a powerful and remarkably precise arrangement hundreds of millions of kilometers away. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.